Hi, my name is Eric Enga. I got interested in Git about some years ago. It became apparent to me early that this was the future of version control. Still, I left it after frustrations and I started trying Mercurial instead, which seemed a lot easier. My friend who had introduced me implored me to give it a second chance. I did that and I haven't looked back since. My problem, which I believe is most people's problem with Git, is that the user interface is very complex and it looks like it's made by geeks for geeks. Last time I checked, I think there was 152 different commands. And they each got a lot of switches. So that's a lot of complexity. And that's what turned me away from Git initially. Reading the man pages was next to impossible. But why did I not give up, and why am I happy with Git today? Well, I started reading the Git community book, and that gave me a realization. We love to use car analogies. I'm going to do just that now, even though the analogies are, often broken in important ways. Let's try. So CVS, Perforce, and Subversion. These version control systems, they're kind of like a modern Mercedes. They expose a shiny surface and they're easy to use. Git, on the other hand, is different. It's more like a T-Ford. And that isn't very flattering. It has a clunky exterior. The key with Git, though, is to not look at the interface, but to look under the hood. If you open the hood of a T-Ford, it's a lot easier to understand than a modern Mercedes. Git may have a complicated interface, but it has a much simpler data model beneath the hood than Subversion, SVN, Mercurial, and all these other traditional version control systems. Well, Mercurial isn't quite traditional, but I think it's still a bit more complicated how it works. It was when I read the Git community book I realized this, and that all the different pieces fell in place. The data model is the key to understanding Git. So why is the exterior of Git so complicated and the model so simple? Well, Git isn't your normal version control system, but more like a set of tools for building one. This means that the lower level pieces used to assemble Git often gets partially exposed at the surface. It's what we call leaky abstractions. These are the pieces which are not meant for the end user, but it is this modular construction which helps give Git its flexibility. To understand this, it's worth noting that originally Git wasn't really a version control system, but more like a file system with a set of tools which let you build a version control system on top of it. To understand what I mean by a file system in this context, let's look at a normal one. Let's look at a Unix file system in particular. And a Unix file system is made up of different objects. Each object has, for instance, a name, for instance, foo.txt, and it has a unique identifier called an inode. The inode numbers are running serial numbers. Each object is usually one of two types. So we either have a file or we have a directory. Technically, everything in Unix is a file. The files and directories can form hierarchies of any complexity. While a file is uniquely identified by an inode, the user locates files using a location, and that's why it's called a location addressed file system. I can give a path to locate a file. The interesting thing is that multiple paths can lead to the same file. In fact, the file can have different names. I can change the files and they keep their name and inode. Now let's look at the Git file system. It has a lot of similarities. Again, we have a name, but instead of an inode number, it has a SHA-1 hash. I'm going to explain what a hash is in a moment. In addition, we have different types, blobs and trees. So these kind of corresponds to files and directories. Together, just like with Unix, Git, blob, and tree objects form hierarchies, and the same blob can be referenced by multiple trees. But we don't talk about paths with Git. It's not content address. It's not location address. Rather, it's content address. The SHA-1 isn't a running serial number, but computed by taking the contents of a file and running it through a SHA-1 hashing function, which gives us this SHA-1 hash. So regardless of the size of the file, we're going to get this fixed length string of characters, which forms a unique identifier for this file. So basically, a file with a different content will produce a different SHA-1 hash. Now, theoretically speaking, there is a certain chance that two different files could give the same hash, but that's considered very implausible. One of the implications of this is that you can't change the content of the file without changing its name, which again means that Git objects become immutable. I'm going to show you how that works by taking you into the .git directory, which is where Git stores all the information about what you're checked in and so on. So we're going to look at what happens with the blobs and the tree objects. So you probably already know how to create a Git repository. You write git init. If we look inside this .git repository, inside the subfolder called objects, you can see it has an info and pack when these are empty at the moment. So we can't really see any blobs or trees. So let's fix that. We'll do this by creating a regular Unix file named new.txt, and we'll fill it with the line new file. We're just using echo for this. At this point, Git doesn't know anything about our file. We have to tell Git about it with git add. And this adds it to the Git repository. Now, you've probably done this before multiple times if you use Git. But do you know what actually happens inside? Well, let's add the file and look what happens. So we get this new directory called FA, and there's a file there with a long name. That looks an awful lot like a SHA-1 hash, which is what it is. Except Git has chopped off the two first characters in the SHA-1 hash, which is FA, and so it's a kind of optimization to not get loads and loads of SHA-1 files right under objects. It's placing them under different directories based on the first two numbers or letters in the SHA-1 hash. Now, you might not believe me that this is actually the file, but Git has a command that lets us basically cat things in our file system, in our Git file system, which is git cat file. And then we give, with the p-switch, we give a SHA-1 hash, and we don't have to write out the whole hash. It just is enough that we have enough characters to uniquely identify the SHA-1 hash that we're interested in. And you can see that at the output that we get new file, which was the content that we put in this file. Let's create another file and add that. And you can see we get another entry in under objects. And now with this command, I'm changing the content of test.txt, and I'm adding this change. So add isn't really for adding files, but for adding changes. And the interesting part is that we don't update the file. You're seeing we're getting a new blob. Whereas if you do ls in our Unix file system, you can see there's just still 2 files. Now we haven't created tree objects yet. The way you can do that is with git write tree. Now remember, none of these commands really are things that you want to learn. So don't write these down and memorize it. This is really just to inspect and understand how Git works internally. These are very low level commands and not really suitable for doing version control. This is basically sort of the primitive operations of the Git file system. So write tree takes everything that's in the index, or what we call a staging area, and it puts all these blobs under a tree object. So what you see here highlighted in blue is this new tree object, and we can look at that with the cat file command. And you can see the content of it. It contains 2 entries. So this is basically a directory entry. It says it has new text and test.txt, and it says what the SHA-1 hashes of these are. And the second column says blob, so this indicates what kind of type it is, whether it's a blob or whether it's a tree. So this is what we created so far. This is what it looks like inside the Git object repository. So one thing I want to talk about is that if you change a file and add that change to Git, then we will create a new blob. So let's look at this example. What does that cause when you're changing a blob in a tree structure like that? So assume we're changing the blob B3, but basically we're making a change to the file that was stored in B3. That's not going to replace B3 because the SHA-1 will change, so we're going to get a B3 marked. Now, T2 can't point to B3 marked anymore because that's going to have a different SHA-1 hash. So we're going to have to get a T2 marked, and T1 can't be pointing to this T2 marked either because that's going to have a different SHA-1. So we're going to get a T1 marked. So what happens in Git is that when you're getting a change far down in the hierarchy, that change kind of bubbles up. So wherever some change happened, the top node in the tree will be replaced with a new one. I just want to give you a quick overview of what a regular version control system looks like compared to Git. On the top, we've got the structure of something like Perforce or Subversion. It's based on storing the delta of individual files for each check-in. Also, you can see files live a kind of independent life. They're not directly attached to a check-in. In Git, however, each commit points to a snapshot of our quote-unquote file system of what it looks like at a given time. So you can see that, for instance, in commit C2, you got like a delta 1 and two deltas. But in Git, that would correspond to getting 2 new blobs, A1 and C1, which are the mutated A and C. Whereas B remains unchanged, so it would point to the same B. So a git commit is basically another blob or object in the Git object store. And it points to a tree object. So commit contains who made the change, when it was made, and what was changed. So what is essentially the tree it points to. So I want to show you what exactly a commit is in Git and a branch. So basically, let's look at it a bit more in detail, and what do we actually see in the files themselves. So for this, I'm just going to create some more example stuff to work with. We're creating a new directory called back, and go into that. And I'm creating a new file, test.txt. I'm using the content of a previous file stored in the Git repository. So if I cat this file, test.txt, you can see I'm storing a version 1 in it. And then we're adding that. So the interesting thing is we're basically adding a file with the same content as an existing file. So you can see how you can point to the same blob through multiple tree objects. So this is the command you should be used to, git commit. We're giving a message. So this commits all the changes in the staging area. So what does actually a commit do? Well, you can see that it creates 2 new objects in the object store, and we can look at these individual objects to see what actually happens under the hood when you're doing a commit. So if we do a git cat file, you can see here we got the SHA-1. So in the git commit message output, you can see that it gave information about some SHA, and this is the same one that we're catting here, and it's the same one that you can see popped up in our object store. And you see the content of it is really simple. So a commit is really just this simple plain text file that it says which tree it points to. So that's the SHA-1 of the tree, and that's the one that you see up here in the object store. And then we have the author and the committer and so on. So commit just creates a commit object and a tree object that points to the various blobs that we have added to the object store. So pretty simple, actually. So this is now the current state of our Git repository. We have a single commit, it points to blob. And remember, we created a new directory back, and then we added to that a file that had the same content as a previous one. So let's talk about branches. Head points to the current branch, and branch is a label on a commit. When I started Git, it wasn't really clear to me what these things meant. Like, what do you mean by a label? I think it helps a lot to just see what these things are under the hood, because then it's very obvious what they are. Branches are really just files. So we can start by looking at the git head file. So that's just the definition of our head. And if we cat that, you can see just a single line that says ref/head/master, and that's actually a path inside the Git repository. So you can see here at the bottom it says refs, heads, and master. So that's actually a location inside the .git repository. And we can look at this location, and that shows us the SHA-1 of a commit. So that's really all that a branch is. It's a file that contains the SHA-1 of a commit, and it exists. It can be placed under different subdirectories depending on how it's organized. The head subdirectory are typically the path, the branches that you're working on. So let's add a line to our existing file, test.txt. So we do a cat, you can see that that's the extra line. And if we do a commit with the -a or add changes of files that Git is already tracking that have been changed. So you can see it says one file change and one insertion. And now if you look at master, you can see that the SHA-1 has changed because we got another commit. And this SHA is, we get a message about that when we run the git commit command. So the Git repository is a directed acyclic graph. So that's a graph with no cycles, but nodes may be shared. One thing I think is useful to know about is the difference between tags and branches. Well, you probably know kind of conceptually the difference, but it's useful to know how does that work in Git. So imagine that we have checked out master, so that means that head points to master. When we make multiple commits, we move like this. However, if we do a checkout version 1 and version 1 is a tag, as we make commits, the head will move like this, but the tag will stay in its place. And one thing that's really useful to know about is detached head, or how you probably get lost a lot of times. So if you check out a particular commit, so git checkout 1D05, then head will point to this rather than the right. And this is something that I've seen people accidentally do in GUI tools. So they want to check out a branch, and then instead of clicking on the branch and checking that out, so say checking out master, so you want to have head point to master, you're checking out the commit. So what happens then is you start making new commits head moves, but there's no file in Git really that's storing these SHA-1 hashes. So if you should move heads to some other location later, you kind of lose your commits. Or they will still be in the object store, but you have a hard time finding them again. While we're looking at what happens when we're moving back and forth in commits, let's look at resets. So that's a way you can undo mistakes. But you got to remember, never ever do this on published commits. By published commits, I mean things that you have pushed to another repository that other people are working on. Now, if you are the only one working on it, then okay, that might work fine. But generally, try to avoid that. So we write the git reset and a commit, and then we'll move back to that commit. And if we start doing more commits, we'll basically end up with a branching like that. So different kinds of resets. We've got soft reset, so that's the safest one. That keeps the working tree and the index unaffected. So the index is what I also refer to as the staging area. This is where all our changes are. Basically, it's like all the blobs that we have added to the repository but that are not part of a commit yet. With mixed, then the working tree is unaffected, and hard discards all changes. So that's kind of an undo. You're just throwing away all the stuff in your working repository or in your working tree. Okay, let's look at how you do branching in Git. So if I do git branch experiment, then I'm basically just adding another tag like that. It's going to create another file that points to that SHA-1. I can do a checkout experiment, which will move the head to point to that one. And if we do a commit, head will move experiment over to the next commit. Now we can check out master again, which means we're moving head to point to master. And if we do another commit, you're going to see that we get this sort of what I would typically think about as branching. I think when I started Git, I thought it was confusing that there wasn't actually a branching of nodes, because often you will have labels along just one chain. I want to show you some different kinds of merging. You've probably seen this message of that there's a fast forward merging. So imagine that we create a branch named fix, and then we're checking it out, and we're doing some commits on it to, fix a bug. If we go back to master, we haven't really done anything in master, so if we do git merge fix, it's just moving up there. So this is a fast forward merge. But what's really the big thing in Git is three-way merge. So here you got to imagine that we're doing a unique commit on master, and then we try to merge fix. So then we're getting a three-way merge. So the nodes that are involved in a three-way merge is the common ancestor, that will be this C0, and the commit or the snapshots that we merged into C2, and the snapshot or the commit that we want to merge in. And then finally the merge commit, that's this one, C3. Just a little bit more elaborate example, show you the nodes involved. So it's really key here to know the common ancestor, C2 in this case. So why is the three-way merge such a big deal? I remember when I started with Git, I kept seeing this. I didn't quite really understand what the three-way merge is. But it's one of the reasons why Git is so much better than the competition at merging. So we can compare this with a two-way merge. So we have this original text that contains 1, 2, 3, and 4. And then Alice, she removes the first line 1, and Bob, he adds a line 5. If you do a diff between these two, it looks like 2 lines were added. If you're doing it the other way, it looks like 2 lines were removed. So basically, the two-way merge is clueless about the past. It doesn't really, it gives you the wrong idea because it doesn't really know anything about the past. With the three-way merge, it tells us how the files changed. So in this case, we're doing a diff with Alice and the origin text that tells us that 1 line was removed, and we're doing with Bob and the origin text that tells us that 1 line was added. And this is possible because Git is actually able to identify the common ancestor because it's keeping these arrows to the various commits. So how does it work with remote branches? So imagine that we have a GitHub account and we have these 3 commits up to C2, and we have a master branch here. So we clone this project, and then what happens on my computer is we get a origin/master, a remote branch. So really all that is that if you remember from inside the .git directory, we had these references, and one of them that I point out was heads, and that will be the normal local branches that we work on, and then the remote branches will be under the remote directory. So say we do some commits locally. Meanwhile, somebody else has put 2 new commits on GitHub. So we fetch the origin, and we're left with this branching thing here. So this is the workflow I recommend for working with branch. So from the top to the bottom, the commits represent the most cutting edge and least stable development. So when a feature is finished, we merge it into the development branch. And when development branch is stable, we merge it into master. So typically it's just one develop branch, but multiple feature branches, one for each feature. So this is the most stable one for active development and for new features. One thing that sounds a little bit strange in Git, I think, is called tree-ish. I was a bit confused by this at first when I started Git, but tree-ish is the name of a way used in Git to specify revisions. When you just specify the name of one branch, we get the nodes in that branch. So like this. So this gives these nodes. And of course, we could check the experiment branch. If we use the dot between, then we're going to get the nodes that are, it's basically like a set difference. We're excluding from the set of all nodes, we're excluding the ones in master, so we're only getting the ones that are unique for experiment. And we can do the other way, so we get the ones that are unique for master. And there's even, if we don't have a dot between, then it's like a set union. We're getting all the commits. But if we're doing a dot, it's sort of like an exclusive OR. We're getting only the ones that are different between master and experiments, and we're excluding the common ones like A and B. So tree-ish is quite elaborate. You can specify a lot of stuff here. Git kind of needs this because you don't have these sort of useful numbers on revisions like traditional version control systems. So we can write head at 1 to find out what branch you just switched from. And you might wonder, well, where was my master branch yesterday? Well, you write like this and you find that out. And what's the parent of the current commit? You write head with the hat symbol. And here's a little tricky one. So if your commit had more than one parent, what is the second parent? So this is in the case of a merge commit that would have 2 parents. And this is how you get the second parent. Probably more common is that you want to know, for instance, the grandparent of the current commit, and then you would use the tilde symbol. Now I want to show you some commands for working with Git remotely, because you're typically going to do that all the time. Remote really doesn't necessarily need to be another server. It could just be another Git repository on your local hard drive. But Git remote, add origin. So this is the green is what we want as an alias for a URL, and then after that we're specifying the URL that we want origin to represent. So of course we could call it something else in origin, but that's a convention. So the first part here, that's the protocol. And once you do that in the .git config file, you're going to get an entry for origin that says what the URL is, and the fetch line here says something about which references we're fetching from and pushing to. So references is just a bit more generic than a branch, but it's basically a file that points to a SHA-1 representing a commit. So the first part in red here, that represents the server reference. So we're having a star here, so it says that for every reference on the server under head, so that's like regular branches, we want to put those locally under .git under refs remotes origin. So when you create this alias origin, it's going to get its own directory under refs, and that's where you're storing the individual remote branches. Now that we have origin, we can so when you do git fetch origin master, Git will know that if you're fetching master on the remote repository, then you actually want that to be stored under remote origin refs master, because you didn't say that you wanted it under any kind of different name. So this is going to use the defaults. Now you might want to fetch it to another one, so you can specify it explicitly and say that I want my remote branch to be named my master instead. So this is the remote part, and that's the local reference of where we want to store what we just gotten. When we're pushing, it's all in reverse, so we're specifying what we are pushing locally. So you can see that in this example here. This is the remote branch that we're pushing to, and here's my local reference that this is what I'm pushing from. So I haven't really covered rebasing, subtree merge, git modules, and really just skimmed remote branches, history rewriting, and all sorts of workflows. But I think that the things I went through now is really most important in getting you to just understand the Git data model. Once you understand that, I think most of the things is a lot easier to read up on and just easily just pick up. So let me just recap what I went through. So Git has a really complex interface, but it has a simple data model. And data model is just three objects: commits, trees, and blobs. And branches, they're just labels. And one of the big things about Git is the structure allows three-way merges. That makes merging a lot better. And tree-ish, it denotes a revision. It's just lots of different ways of specifying a particular revision. And it's worth noting that what we call remote branches, they actually exist locally. So you can go into your Git repository and actually look at them. Okay, so that's all about Git for now. Thank you.